The cosmos, a tapestry woven through billions of years, holds its earliest threads in profound darkness. Observing the genesis of galaxies requires an instrument capable of capturing light from the universe's infancy, light that has traveled across unimaginable distances and epochs. This faint, ancient radiation presents a formidable challenge to conventional observatories. The James Webb Space Telescope, JWST, was engineered to pierce this veil, positioned far beyond Earth's atmospheric interference. Its primary mission is to detect the first incandescent glows of stars and the nascent structures that would eventually coalesce into the galaxies observed today. It operates exclusively in the infrared spectrum. The critical factor in observing the early universe is cosmic redshift. As the universe expands, light emitted from distant early galaxies stretches to longer, redder wavelengths by the time it reaches Earth. This phenomenon shifts visible light into the infrared, making it invisible to optical telescopes but perfectly suited for JWST. JWST's iconic primary mirror, spanning 6.5 meters in diameter, is composed of 18 hexagonal, gold-coated beryllium segments. This immense light-collecting surface is crucial for gathering the extremely faint infrared photons originating from the universe's earliest epochs, providing unprecedented sensitivity for deep space observation. Equipped with instruments like NIRCam, NIRSpec, and MIRI, JWST captures a broad range of infrared wavelengths. NIRCam provides high-resolution imaging, NIRSpec facilitates spectroscopic analysis of light, and MIRI extends observation into the mid-infrared range, enabling the detection of even more redshifted and obscured objects. To effectively detect the faint heat signatures of distant objects, JWST must remain incredibly cold. Its instruments are cooled to nearly absolute zero, approximately -266 degrees Celsius. A multi-layered sun shield, the size of a tennis court, passively blocks solar radiation, ensuring the telescope's own heat does not overwhelm the minuscule signals it seeks. JWST's strategic orbit around the Sun-Earth L2 Lagrange point, 1.5 million kilometers from Earth, is fundamental to its operation. This stable gravitational position allows the sun shield to perpetually face the Sun, Earth, and Moon, providing consistent thermal shielding and an unobstructed, stable vantage point for observing the deep cosmos. The process of mapping begins with long exposures. JWST points its mirrors at specific patches of the sky, collecting faint infrared light for hours, sometimes days. This extended observation time allows it to accumulate enough photons to resolve incredibly distant and dim celestial objects, many of which are only nascent galaxies. Upon collection, the light passes through JWST's sophisticated filters and spectrometers. These instruments precisely measure the wavelength of incoming light. By analyzing the amount of redshift, scientists can accurately determine the distance to a galaxy and, consequently, its age at the time the light was emitted. Spectroscopy is paramount. NIRSpec splits the light from individual distant galaxies into a spectrum, revealing characteristic absorption and emission lines. The degree to which these spectral lines are shifted towards longer, redder wavelengths directly correlates to the galaxy's recessional velocity and its distance from the observer. This redshift data allows astronomers to construct a three-dimensional map of the early universe. Each point on this map represents a galaxy, positioned by its observed coordinates and its calculated distance. This provides an unprecedented view of cosmic structure formation just hundreds of millions of years after the Big Bang. The initial light from the very first stars and galaxies ionized the neutral hydrogen gas that filled the early universe. JWST's infrared capabilities allow it to detect the signatures of this epoch of reionization, offering direct evidence of when and where the universe became transparent to light. Gravitational lensing further enhances JWST's capabilities. Massive galaxy clusters in the foreground bend space-time, magnifying the light from much fainter, more distant galaxies located directly behind them. This natural phenomenon acts as a cosmic zoom lens, allowing JWST to resolve structures that would otherwise be undetectable. By observing these gravitationally lensed galaxies, JWST can study objects that formed even earlier and are intrinsically fainter. This technique pushes the boundaries of cosmic visibility, providing glimpses into the very first aggregations of matter, revealing how primitive structures began to evolve into more complex galaxies. Unlike its predecessor, the Hubble Space Telescope, which primarily observed invisible and ultraviolet light, JWST penetrates the cosmic dark ages. Hubble could glimpse distant galaxies, but JWST's infrared vision effectively sees through the obscuring dust and highly redshifted gas that characterize the very early universe, revealing previously hidden structures. The first galaxies mapped by JWST are profoundly different from the grand spirals and ellipticals common today. They appear as smaller, often irregular and intensely star-forming clumps of matter. Their rapid stellar birth rates indicate a turbulent and energetic early cosmic environment, distinct from the more settled galactic evolution seen at later epochs. The stars within these primordial galaxies are inferred to be significantly more massive and hotter than typical modern stars. Their short lifespans and explosive deaths, supernovae, rapidly seeded the universe with heavier elements, a process fundamental to the eventual formation of planets and more complex stellar systems. This contrasts with slower stellar evolution now. The sheer density of matter in the early universe allowed for more frequent interactions and mergers between young galaxies. This rapid growth contrasts sharply with the relatively sedate pace of galaxy evolution in the current cosmic era, where vast distances often separate galactic neighbors and major mergers are less common. Previous theoretical models of galaxy formation often predicted a gradual buildup of structure. JWST's data, however, reveals surprisingly massive and mature galaxies appearing much earlier than anticipated. This challenges established paradigms, prompting revisions in our understanding of how quickly galaxies assembled and evolved in the universe's infancy. Despite its unparalleled capabilities, even JWST confronts the ultimate limit, the very first moment of the Big Bang itself. The cosmic microwave background radiation represents the earliest light detectable. JWST observes the immediate aftermath, but the universe's absolute inception remains beyond direct visual observation, an inherent physical boundary. The vastness of the observable universe means JWST can only sample specific, limited fields of view. While these samples are incredibly deep and revelatory, they represent only tiny fractions of the entire early cosmos. The statistical inference drawn from these windows guides our understanding rather than providing a comprehensive census of every primordial galaxy. The operational demands of JWST are considerable. It generates terabytes of raw data weekly, transmitted to Earth via high-gain antennae. Processing this immense volume of information, calibrating instruments, and sifting through cosmic noise to identify definitive signals requires sophisticated algorithms and extensive computational resources, a monumental logistical challenge. Despite its robust design, JWST has a finite operational lifespan, primarily limited by its fuel supply for station-keeping maneuvers at L2 and the eventual degradation of its components. While currently projected for over 2 decades, this eventual cessation of function marks an inherent limit to its observational tenure in the cosmos. Even with infrared vision, limitations persist. Extremely dense pockets of dust and gas, particularly within galactic nuclei, can still obscure light, preventing direct observation of certain phenomena. This means that while JWST sees deeper than ever, the most enshrouded events in the early universe may yet remain hidden, pushing the boundaries of current detectability. JWST's data has begun to fundamentally challenge, and in some cases, one significant finding is the unexpected prevalence of massive and mature galaxies at very high redshifts. Previous models predicted a more gradual, hierarchical assembly of galaxies, implying smaller, less developed structures in the early universe. JWST's observations suggest a more rapid and efficient formation process. This accelerated galaxy formation implies either more efficient star formation than previously assumed or different conditions in the early universe. Such discrepancies force a re-evaluation of models that describe the distribution of dark matter and the initial conditions that allowed cosmic structures to coalesce so quickly. The discovery of an abundance of supermassive black holes within these early galaxies also presents a puzzle. Current theories struggle to explain how these colossal objects could have grown to such immense sizes so rapidly, suggesting a need for revised understanding of early black hole seeding and growth mechanisms. The very early universe was characterized by extreme conditions. The presence of these unexpectedly evolved galaxies suggests that fundamental physical processes, like the efficiency of gas cooling and star formation, might have been different or more rapid than our current models predict. This requires a re-evaluation of cosmic initial conditions. The discovery of early bright galaxies challenges the lambda CDM model of cosmology, which describes the universe's evolution. While not disproven, these observations indicate gaps in our understanding, particularly regarding the physics of baryonic matter, normal matter, and its interaction with dark matter in the nascent cosmos. The interpretation of JWST's data also involves complex statistical analyses and theoretical frameworks. Potential biases in observation or interpretation, though rigorously accounted for, always exist. Refining these methods and cross-referencing with future observatories will be critical to solidifying our understanding of the early galactic landscape. Despite these challenges, the precision of JWST's instruments allows for detailed characterization of the detected light. Even if initial interpretations are refined, the raw data provides an unprecedented window into cosmic history, demanding that theories adapt to the empirical evidence uncovered in the infrared depths of space. The sheer quantity of data necessitates a global collaboration of astrophysicists. Analyzing observations from JWST requires diverse expertise in theoretical cosmology, observational astronomy, and advanced data processing. This collaborative effort ensures robust interpretation and verification of the groundbreaking discoveries, preventing singular biases. Future space telescopes, designed with even greater sensitivity or different wavelength capabilities, might further refine these maps. Concepts for next-generation observatories aim to probe even deeper into the infrared or to directly detect gravitational waves from the earliest cosmic epochs, offering complementary views to JWST's infrared gaze. The ongoing mission of JWST continuously adds new data points to this cosmic tapestry. Each observation refines the map, pushing the boundaries of what is observable and confirming or challenging previous findings. The dynamic nature of astronomical discovery means our understanding is in constant evolution as more light arrives. The very existence of these distant, fledgling galaxies confirms the universe's dynamic evolution. From a primordial soup of hydrogen and helium, gravity sculpted the first stars, which then illuminated the cosmic dark ages, initiating the complex processes that led to the universe's current majestic structure. It is a testament to the fundamental forces at play. JWST's mapping of these early cosmic structures provides a profound glimpse into our own origins. Every atom heavier than hydrogen and helium, the building blocks of planets and life, was forged in the hearts of these ancient stars and scattered across the nascent universe by their explosive deaths. These first galaxies are the ultimate ancestors of everything known. The telescope itself represents a pinnacle of human ingenuity, a complex machine capable of reaching back across billions of years to capture photons that began their journey when the universe was in its infancy. It embodies humanity's relentless pursuit of knowledge, extending our senses far beyond terrestrial confines to embrace the cosmic past. The data stream from JWST continues to flow, a torrent of information reshaping astrophysical theories and offering new mysteries. Each new image and spectrum pushes the boundary of understanding, revealing a universe more intricate and surprising than previously conceived, inviting constant re-evaluation of established scientific models. Ultimately, JWST's mission transcends mere data collection. It provides a profound connection to the cosmic narrative, a tangible link to the universe's earliest moments. It is an exploration not just of distant light, but of the fundamental processes that govern existence, including our own. As humanity gazes into the infrared depths captured by JWST, witnessing the birth of galaxies, it reflects upon its place within this grand cosmic evolution. What further revelations about the universe's ultimate origins and destiny await in the expanding sea of data yet to be analyzed?